Hey guys, and welcome to my presentation for Dental Composites Ideal for Your Teeth. This is the project for my group for MSc 4793, which includes myself, Charles Taylor, Laura Janinski, and Bree Hines. Each year, 5 million people receive a dental implant to improve dental hygiene and smiles. The ultimate goal for the composite is to replace the dental root. The desired composite characteristics for a dental implant application include biocompatibility, chemical resistance, high corrosion resistance, durability, and to be aesthetically pleasing. Resin composites increased in popularity over amalgams and alloy of mercury in 1999 due to their improved mechanical properties and white coloring. The dental composites showed significant advantages in strength and durability over the prior metal implants and were less damaging for the mouth. Thus, the ultimate goal of this presentation is to demonstrate how the composites are the ideal material to produce dental implants with and provide strength and wear resistance. As a background, early civilizations used carved ivory and gold ligature wire to restore natural teeth. If we fast forward to the 1980s, silver became the most frequently used restorative dental material. But they found when patients chewed, mercury vapor was released, which is very toxic to the body. Additionally, the silver was not aesthetic. Today, dental composites are utilized for their superior mechanical properties, biocompatibility, and aesthetic nature. Dental composites are used to replace a structure of missing tooth material. This can be in the form of cavity fillings or implants. Dental composite resins are composed of an organic polymer matrix, inorganic filler particles, coupling agents, and an initiator-accelerator system. Some common organic matrix materials include BIS-GMA, TEG-DMA, UDMA, and BIS-EMA. But for this presentation, the focus will be placed on UDMA, or urethane dimethylcrylate matrices. For performance requirements, in order to serve as effective dental implants, the composite selected for this role must be able to meet several key performance requirements. It must have chemical resistance to withstand acidic food/saliva. It must have mechanical strength in order to deal with chewing/crushing. And it must have wear resistance in order to not be worn down by eating over a long period of time. The raw materials that are required to produce our dental composite include the following. UDMA, which is the organic polymer matrix as shown in Figure 2, NCAP, etc. are inorganic additives to prevent disease and bacteria from attaching to the composite. The silane coupling agent is used to increase chemical interfacial adhesion as shown in Figure 3. UDMA will be analyzed in its application to dental implants. It is the highest rate of polymerization, low viscosity, and flexibility. UDMA has a dense polymer network in comparison to TEG-DMA and BIS-GMA. Polymerization shrinkage, modulus of elasticity, and solubility are the largest problems associated with the organic polymer matrix. Inorganic filler particles are added to the polymer to prevent disease and bacterial attachment. Common inorganic additives to UDMA include NACP, CAF2, BAG, HA, FA, and BN. Depending on amounts of additives, the properties shift slightly. It is important for the pH balance to be maintained, as mineral loss is initiated at 6 to 6.8 in the root and 5.4 in the enamel. In order to increase the mechanical properties of the polymer matrix with inorganic filler particles, silane coupling agent increases the chemical interfacial adhesion. Surface pretreatment is necessary to ensure durable bonding to the resin. Lastly, the initiator-accelerator system cures the composite by utilizing a chemical reaction or light. All of these aspects combined allow composites to be the ideal material for dental implants due to the properties listed in the image, including but not limited to biocompatibility and mechanical properties. While the bulk of composite structure is the organic polymer matrix, there are other components as mentioned in the prior slide. The organic matrix forms the base of the structure of the composite. The manufacture of the composite, the following steps occur. First, polymerization, where the organic polymer matrix along with any additives and coupling agents is mixed together to form a composite resin. In step 2, the inorganic filler particles are added to the resin mixture. The amount of filler particles can be adjusted based on the desired properties of the final composite. After that, the surfaces are treated to ensure proper bonding before application. The final step in the manufacturing process is curing. This is when the initiator acceleration system is activated, either chemically or with light, to initiate the curing process. This solidifies the composite material until its final form. Economically, the cost for users of restorative dental procedures is highly dependent on the time commitment and material cost for composite resin fillings. In terms of material cost, the price is mainly reliant on the type and depth of the cavity, with the brand of resin playing a minor role in total costs. Average direct material costs for composite fillings are approximately $8, which includes procedure equipment and the resin itself. For the user, composite resin fillings can cost anywhere between $100 and $500 per tooth. These costs depend highly on the complexity of the procedure. The global dental composites market value in 2022 was valued at 59.7 million, with projections to reach over 100.4 million by 2031. The market for composite dental work is widespread and only growing. The main market includes dental professionals, labs, and patients. Dental professionals primarily use composite resins for implants, crowns, and bridges, and dental labs fabricate restorations using composite materials. Patient motivations involve seeking a durable, natural-looking implant or filling for dental restoration procedures. Major manufacturers of dental composite projects include Ivoclar, Vita, 3D Systems, Dentsply, Sirona, and Care. These companies and more are furthering research and development of these products in both materials and innovative technologies. New developments related to dental composites include new resin formulations and improved processes that minimize the release of monomers from the dental materials. In choosing a resin for dental composites, factors that must be considered include viscosity, degree of monomer conversion of the polymer matrix, polymerization shrinkage, water sorption, and mechanical strength. These factors determine the ease of application and how quickly a dental composite will be degraded through daily use. Degradation of dental composites is an important focus in research, as the breakdown of resins can release harmful monomers into the user's body. To combat this, a novel resin was formulated with better mechanical properties than current dental formulations. This resin is an MEDBI-based UDFA with TEGDMA. Further research into the functionality and feasibility of this formulation must be done in the future. In terms of processes, the type of light source used for photopolymerization or curing, as well as the time that the resin was left to cure, are important for decreasing the amount of harmful monomers released by the degradation of the dental composite. Studies revealed that the best results for limiting degradation were found with longer resin cure times, the use of diode lamp as opposed to a halogen lamp for activation. Dental composite resins are the most widely used restorative dental material. These resins are able to restore the physical integrity of damaged teeth, most commonly through fillings or implants. When compared to other dental restoration materials, composite resins have a higher degree of wear resistance and less shrinkage, which can lead to product failure. Another benefit of composite resins is the natural aesthetics they provide, as they are available in a range of colors. However, research is still needed in improving these materials. They are still prone to failure through shrinkage and adhesive failure. Another major concern that must be addressed is potential for user exposure to harmful monomers as the resins degrade over time. And that was our presentation. Here are some sources, and thank you all for your time.